Amanda project. Hopefully you will be able to see my screen. Okay, so first of all, a few words about the project and starting with the motivation of the project and why the project has started and it's in progress. So the world is undergoing a digital transformation and we're generally looking for different ways in order to provide innovation. There is a growing need for a sophisticated approach to solve problems in different categories. For example, in the area of smart cities, for air quality monitoring, for temperature monitoring, for humidity, for noise and occupancy detection. For people and asset security, for example, for imaging, for tracking, for data privacy or cybersecurity, and also for ways in order to mitigate the different effects of the COVID-19 pandemic. So imagine if there was an intelligent system with very small dimensions, a very small thickness, and ultra low power consumption that can be easily installed or even used by users as a wearable, and that has a maintenance-free lifetime of more than 10 years. And this is such a project, the Amanda project. Also, let me have a small stop here, and you have seen that there is a feedback pop-up that appeared in your screens. There are a few questions that it will be very helpful for us if you could answer them in order to help us assess the outcomes of this webinar. So what is the Amanda project? It is a European multinational collaboration. It includes 8 different partners from 6 different countries in Europe. These are Belgium, Croatia, Greece, the Netherlands, Switzerland, and the UK. The 3 of the 8 partners are from the academia, and these are the Center for Research and Technology Hellas, that is also responsible for the coordination of the project, IMEC from the Netherlands, as well as the Zurich University of Applied Sciences from Switzerland, and also 5 different SMEs and industrial partners, and this include Lightricity from the UK, EPIS from Belgium, Elica from the UK, Microtool from Switzerland, as well as Penta from Croatia. So this is the concept of Amanda. Our focus is, first of all, on miniaturization. We are designing and developing an embedded system with the dimensions of a credit card and a thickness that is not exceeding the 3 millimeters thickness. We are developing and optimizing an advanced sensing technology. We are focusing on ultra low power consumption and on energy autonomy for all the different electronics in the card, the energy harvesting components, and also the energy storage components. We have included in the card different wireless communication capabilities, including short range and long range communications, ultra low power localization, as well as asset tracking. And finally, we are focusing on the intelligent aspect of the card, including sensor and data fusion, low power edge intelligence solutions, and cybersecurity. So this is a conceptual view of the Amanda card. In the center of the screen, you can see the MCU, the processing heart of the system. A photovoltaic energy harvester is included, different wireless components, and different sensors and other actuators and components. And also here you can see a conceptual view of the outside layer of the card and of the packaging, including cutouts for the energy harvester, for different sensors, and also for the image sensor of the card. The hardware infrastructure of the card can be categorized in 3 different layers. First of all is the sensor and edge intelligence layer that includes all the different sensors that are developed as part of the project and a few of the self-sensors. Second is the wireless and security layer that includes all the different wireless technologies and protocols. And third is the energy management, including the energy harvester, the power management circuits, and the rechargeable storage elements. So these are the list of the innovative components that are developed as part of the Amanda partners and as part of the Amanda project. First of all, an ultra-thin, ultra-efficient photovoltaic energy harvester by electricity with a very small footprint. An energy storage from Milica, a miniaturized solid-state lithium-ion battery. An innovative power management integrated circuit from EPS with a very small system footprint that manages the energy that is provided by the energy harvester, and it's responsible for its circulation throughout the card and the provision of this energy to the different components of the card. A capacitive sensor from Microjoule, a lowest active power touch switch that is able to measure absolute capacity. A temperature sensor, again from Microjoule, with a very low power consumption and very minimum dimensions. A fully integrated QVGA CMOS imaging sensor from EPS with a very low power consumption, as well as different software components. And this includes a data fusion component for the collection, cleaning, pruning, and indexing of the data that are collected from the different sensors of the card. A cybersecurity software component that offers hardware and software protection against different cybersecurity threats, and an edge intelligence software component that is used for different AI and edge intelligence capabilities. For the wireless communication aspect of the card, on board of the card, there are included 3 different solutions: a Bluetooth low energy, that offers a very low power consumption and short-range communications. An NFC IC that also enables the short-range communication of the card, but also offers for a wireless charging of the battery of the card. And finally, for long-range communications, we have included a LoRaWAN circuits. So this concludes the very brief presentation of the Amanda project and our motivations and the different technologies that the card includes. So I would like to pass the presentation now to Dennis Passero from Milica for a short presentation of the different use cases of the project.
Hi, everyone. Let me share my screen quickly. Okay. I'm Denis Passero, product manager at Milica. I'm going to take you through the use cases and scenarios that we're trying to meet in this project. So we've designed the Amanda autonomous smart sensing card to meet the requirement of at least 6 scenarios listed here and 3 use cases. Number 1, environment monitoring and reporting. Number 2, assets tracking and occupancy monitoring. And number 3, mitigating the effects of the current pandemic. There's a lot of information about these use cases and related video and collaterals on our website. I invite you to look at this if you're more interested. But today we're going to be focusing on scenario number 1. This is indoor environment and thermal comfort monitoring. So in this scenario, the card is installed outdoors or in a room, or is a wearable. After the initial configuration by the system administrator, it can provide measurements related to heating, ventilation, and air conditioning. The card can also serve as a weather monitoring station. The wearable version can also be used for thermal comfort monitoring. The card automatically informs a room controlling system to adjust the heating, the ventilation, or a room conditioning controlling system to adjust the heating and ventilation. An application installed in the end user's smartphone, for example, can project the room's or the outer environment's conditions in real time, as well as the thermal comfort level of the users. I have a short video to illustrate what I've just been talking about. And there it is. Okay, and this ends the section on use cases and scenarios. I'll invite our partner, Martin Schellenberg from Microdoor to give his own presentation. Thank you.
Yeah, thank you. I'll just share my screen. Hello, so also from my side, I'm Martin Schellenberg from Microdoor in Zurich in Switzerland. I'm working at Microdoor. Microdoor is a SME with about 90 employees in the center of Zurich. We have modules and thick film business with a production line in-house, and we have a fabless semiconductor department where we design ASICs and standard products. Now, our contribution to Amanda is consists of two ICs. One of them is the temperature sensor, the MS1089, and the second one is a capacitive sensor. So in the following, I will first give a few more details on the thermal comfort monitoring scenario, where the temperature sensor plays a crucial role. And after that, I will introduce you to the temperature sensor itself and give you there a few more details. Now, concerning the thermal comfort scenario. So thermal comfort is basically the subjective evaluation of a person, how at ease he or she feels with respect to the thermal environment. And several factors are playing a role and define this thermal comfort, like the ambient temperature, the airspeed, humidity, also the clothing, the physical activity of the person. So in the implementation of this scenario in the card, basically the software is following the ASHRAE 55 standard, which defines a few terms and defines a few equations. So it's based essentially on the predicted mean vote, which is a scale between subjective feeling between very cold and hot. So from -3 to -3 to +3. ASHRAE defines a calculation based on parameters like air temperature, radiant temperature, airspeed, and so on. So several of these parameters can actually be measured by sensors on the card. Other parameters have to be estimated and are, for instance, depending on the environment. So where the card is used, if it's indoor, if it's in the sleeping room, if it's in the car, and so on. So essentially, the card is using several of the sensors to estimate, to get readings and calculate this PMV value. And this is the list of the components that are actually active in this scenario. And as you see, the temperature sensor from Microtool will play a role here. Then on the software side, we have the sensor readings, the data fusion, and the Edge Intelligent, which is computing actually this thermal monitoring value, or and then if there is an improvement needed, it will send a message over the RF to the air condition. So that's about what is going on in the thermal comfort monitoring scenario. And now I go a bit closer to the temperature sensor that we have developed. So silicon temperature sensors, and there is a lot of different types on the market of them. They are all basically depending on the forward biased silicon diode, which has a directly a linear dependence, so that the diode voltage or the base emitter voltage of a diode connected bipolar transistor has a linear dependence on temperature. But then there are many ways of converting this information to digital values, so to actual measurement values. So all these implementations are differing in the measurement electronics, like so there are oscillator-based sensors or direct AD converters and so on. Then it's also important to get the linearity correction, because all these elements on the electronic circuit often are not ideal and are not completely linear. So there are electronic measures also to correct for this linearity, to get a good accuracy over a large temperature range. Then there is a lot of spread in these parameters as well. So there is normally a calibration needed per device. And all these different implementations result in different power consumption. So usually if a very high accuracy is required, the power consumption goes up as well. Or if a frequent measurements are required, then the power consumption goes up. So essentially, Microtool has a lot of know-how in this area, and we have already developed several temperature sensors and monitors. And also for the new one, for the Amanda project, we are basing this on an existing design. But initially, we started with a state-of-the-art analysis. So we looked at the market and we compared a lot of parameters, and we decided to concentrate on the smallest power possible. So we wanted to be the best in power consumption on the market. And we also concentrated basically on a small solution, because that's also an important aspect for the Amanda card. So as you can see in the table, so we looked essentially at a relatively slow measurement rate of 1 measurement per minute, and wanted to beat all the market in power consumption, average power consumption. So we're talking here about nanoamperes, so that's already quite low. Now, what were the methods to reach this low power consumption? Basically, we had 3 approaches. The first one, we introduced several resolution settings. So with 3 resolution settings, we were able to get a very good accuracy for the calibration, because we are measuring in the best accuracy setting or best resolution setting to get a good accuracy. But on the other side, if the calibration is okay, we can actually measure at a lower resolution, which shortens the measurement time and reduces, therefore, the power consumption. A second approach was to reduce the power consumption, the active power consumption during the measurement, by just circuit optimizations. And the third essential part was the reduction of the static current between the measurements. So when the chip is basically idle, we wanted to save as much power there as well. So in the new device, we are completely shutting down all the circuit parts between measurements. So only a small leakage current will be left. And an additional goal for the Amanda ASSC for the card was to extend the supply voltage range down to 1.8 volts to fit the supply voltage of the card, and also to be able to offer 1.8 volts to the market, because that's an important system voltage as well. So after the design, we went to fabricate the wafers, and we packaged the ICs first in a SOIC prototype, which is quite a large prototype. You can see the actual chip inside here. In Microdual, we were able to bond this directly into the package, so we didn't have to go out the house. So we had a very fast assembly and a very fast possibility to evaluate the device. And we also delivered this type of prototype package to the Amanda system for integration of prototypes. But in the end, and we are just preparing now the miniaturized CSP packages. So this is very small. It's basically only the chip with solder balls below. We will deliver that to the Amanda miniaturized card, and that will be ready just beginning next year. And also for external customers, we will be ready to deliver samples in the first quarter of next year. So from the evaluation results, we can see here on this graph on the top left, we see the measurement accuracy. So we see that we have met the specification here with this device. On the right side, we have some measurements of the standby current, so the idle current. So this is just typically 4 nanoamps when the device is waiting. And here we see that we have reached 27 nanoamps of average operating current when we measure once per minute. So in summary, we can say that we have achieved all the goals with this device for the time being. Just a few application hints as well. So besides for the temperature measurement, we can do it basically in 2 ways. So we can control it completely with I2C by sending a command to start the measurement and sending a command to read the result. But we can also use a handshake line. So it's a digital line called TM. And by just sending 1 pulse, the IC will start measuring, and the IC will then pull down the line when it has finished the measurement, and then the controller can just read the temperature out over I2C. So this is the most efficient way of using the device, because even the energy used in the I2C command can at least for the start command can be saved. On the right, I just have an application hint that for fast adaptation to a changing temperature, it is best to isolate the sensor. So here the sensor is in the QFN package to isolate it thermally from the environment. So this last slide is just summarizing again all the features that I just mentioned and parameters. And I would just like to hint you at our website to get further information. So thanks for your attention, and I will pass the microphone now to Dr. Julien Campos from Lightricity.
Thank you, Martin. So let me share my screen. This one. Can you see my screen? It's okay. Okay, so my name is Dr. Julien Campos. So I'm lead technologist at Lightricity, and today I will present you photovoltaic for our photovoltaic energy harvesting component for miniaturization of IoT devices in the framework of the second webinar of Amanda project. So Lightricity is a spin-out from Sharp Laboratories of Europe. And we have established, after 4 years of intensive research and development on energy harvesting and IoT device, we're ready now to commercialize our unique IP-protected indoor photovoltaic PV technology. By PV technology, what I understand is not exactly the same conventional PV that we can see at rooftop of houses with big appliances. By photovoltaic energy harvesting, what I understand is indoor PV energy harvesting to power IoT devices, wearable assets like watch, small sensors that don't need any connection to the AC plug and that are typically powered by silicon battery. So what we offer is a sustainable, environmental friendly PV energy harvesting component. And we also develop subsystem and system, all in all, to eliminate the need for battery replacements. So typically maintenance battery cost for IoT device and sensors inside building. Here we have one issue when we consider that most of the market now today is IoT device powered by primary batteries, is that for some projection, when we look in the future, some projection about, for example, 1 trillion of IoT device in the world. That was one of the projections, for example, in 2012 by IBM. And there is a problem with that type of scenario is that when you have primary batteries, so that means that you need to replace them. And if we consider this 1 trillion scenario for 3 years battery on the table on the right, that will tell you that in this situation, you need to replace roughly around 1 billion of primary cell every day. And it requires such a high level, a very great number of maintenance guys. So that's not realistic in terms of human resources. So there is a very high demand for IoT devices, but there is this upper limit that prevents it. So what we offer on our side is kind of an alternative to the primary cell, is an equivalent a component that will play the role of a primary battery, but which has the advantage to have a very, very high lifetime, more than 20 years expected. And in that case, you don't have any more this problem of maintenance. So by maintenance, in terms of primary battery here, as we provide up to 6 times more power compared to a conventional PV silicon-based material, and with a very, very long lifetime. So with such power, what it represents, for example, a 1 centimeter square electricity PV energy harvester at 1000 lux. So 1000 lux is what you can find in the supermarket. So that's exactly the same energy provided than 5 AAA batteries. So that will be exactly the same energy as 15 IoT devices that will be powered with CR2032 silicon, and equivalent as well among these 10 years as 110 CR1025. So that represents a huge saving on the maintenance aspect. And in that sense, we can see in this specific approach that this component is kind of a financial product. So there's also another benefit, which is the environmental aspect. So if you have no more all this battery to replace, that means also you don't need to throw them to waste. So that's a huge benefit in terms of resource. And that also encourage, because if we are benefit for primary cell, that's we can also work with a secondary battery in that case to top up the secondary battery. In that case, that encourage the recycling model. So other features and other benefits of our technology. So as I mentioned, so we have 3 to 6 times more power per area. So the key number to retain is 20 microwatt per centimeter square at 200 lux. We have, compared to PV silicon-based technology, we still maintain very, very good performance in low, very, very dim environment, below 10 lux. So that means that in this very dim environment, we can maintain applications. We have a material that is very robust with a proven reliability, and also it can withstand very high temperature. So for in harsh environment, in very specific environment with 150 degrees, so it will continue working. It's scalable in the sense that it's completely compatible to mass manufacturing. So for example, pick and place machine, reflow oven, and so on. So that's very interesting to do also some saving on the cost. So there is no handheld manipulation. Everything is done by machine. It's perfectly matching the LEDs and CCFL lamps. So that's perfect for indoor environment where this type of lighting source are majority. It's environmental friendly, as I explained before, because we have less waste battery of the primary, especially. In terms of design, we can do pretty what we want. We have, of course, typical square or rectangle shape, but we can do also circular shape. It's also very aesthetic with fully black appearance, and because we provide 3 to 6 times more power, that means that we can reduce the size by the same area. So that's perfect for ultra miniaturization. And in terms of implementation, so that's for electronics design part, so that we are in multiple of 1 volt, so we can do serialization, and that's very good in terms of to work with that type of voltage. So here just a graph to show the comparative in terms of power generation at 200 lux per centimeter square. So with around 20 microwatts, so that means that we are 3 to 6 times more efficient, and we provide up to 6 times more power than conventional PV silicon-based technology. Here, different lighting conditions. So just a brief word to say that, so typically there are 3 types of level, lighting level to consider. So 200 lux is like in a house environment, but from below 200 lux, we are in dim environment. At 500 lux, we are in office space, so that medium environment, and at 1000 lux and above, this is what you will find in supermarkets. And so what is interesting is that in these different lighting conditions, we are completely linear. So that means if you provide 20 microwatt at 200 lux per centimeter square, so we will provide, of course, 40 microwatt at 400 lux for 1 centimeter square, etc. Here you can see just an amorphous silicon example. So you can see that, so of course, the lower performance, but the power aesthetic as well. And in terms of implementation to your circuits, that's not very convenient because you have typically wires. So that means that you need to solder it. So that's a longer process, and you may have less possibility to control it and to have a more quality product. Here is just a complete generic IoT device, but here with energy harvester integrated. So what you see, you have two main blocks on the bottom and the top. So on the bottom is everything about the power management unit. So it starts, of course, with our PV energy harvester. Then you need a chip or block that is here to extract the maximum of power in a very efficient way out of our energy harvester. And in case like in the Amanda project, so you have a Elica secondary battery. And so you need to charge in a very safe way. And then this power management will extract the energy of the battery and will provide regulated output voltage to what on the top here is called loads. So on the Amanda project, you have 3 types of loads. So you will have the multi-sensors module. You will have, of course, the microcontroller units that is here to treat the data, and you will have then the communication with LoRa and BLE that will communicate all the data from the sensors to a gateway. Apart from Amanda projects, we are also involved in the SBRI funded project, so we are leader in that one. That includes with the partners Sony, NHS Hospital, and other end user partners. So the idea is here in the case of a hospital, so you have many assets of high value, hundreds and more. And some studies just show that in a lot of time is wasted by the nurses and doctors to look after these assets. And the idea is to put a real-time location system, a beacon system, but you stick to these assets. And like this, you can monitor on the hospital, where are they? What the advantage of using electricity in that project is that instead of having 100 or 1,000 of these beacons that are battery powered and then you need to replace every 2 years or 3 years, in that case, we don't care anymore about the battery replacement. It's here to last a very long time. Here our project prototype lineup that we proposed. So that's the first generation. So you have the EXL10 with 170 microwatts at 200 lux. So that's roughly a 10 centimeter square module. You have the EXL2 that we propose for prototype evaluation as well, with around 50 microwatts at 200 lux. And here it's just an example, but we can do any type of shape, as I mentioned, and any type of size from the millimeter square to centimeter square. So for very specific application and specific customer requirements, we can do, for example, here a circular shape, and we can do any type of voltage. So just customer contact us, and then we have a discussion with what they want. We also do so subsystem. Here, what you see is a 4Everlast 1.0. So on the back here, it's not visible, but on the back, you have a EXL10, and this one is with a power management system that you charge in a safe and efficient way. Here, a secondary silicon battery, and then you provide the power to your load. So it's just for companies who doesn't have the time or the will just to develop these subsystems. So that's something that we can do. The new project prototype lineup that we promote now is also the EXL1. So now we go very deeper into the miniaturization. With the EXL1 here, roughly around 1 centimeter square with a 1 volt output voltage at and the output power at 200 lux, which is around 20 to 22 microwatts. You have the EXL 0.25, so the dimension is 5 by 5 millimeters square. So very tiny with a 3 volt output and around 5 microwatts power generation to 200 lux. And the tiny PV module, which is the EXL010 with a 3.5 by 3.5 millimeter square, so roughly 10 millimeter square, with around 2.2 microwatts. And here, the current generation of the 4Everlast, so that's the 4Everlast 2.0. So the same idea as the 4Everlast 1.0. So you have our PV module. So here you can place a EXL2 or EXL1 or EXL2 and the EXL1, and you have different configuration in terms of output regulated voltage, 1.8 volt or 3 volts. That can be configured without a problem. So to summarize, we have eco-friendly, fit and forget project in the sense that it avoids primary lithium batteries, so you don't have to be worried about the battery replacement, primary battery replacement. We have the highest PV performance and reliability on the market with 3 to 6 times more power than conventional PV silicon based components, and also the performance that is maintained on the full lighting condition. So we can, by 3 to 6 times more power, so that means we can enable new functionalities than what was possible before with previous technology, but we can also go further into the miniaturization with very tiny self-powered IoT devices. We have a superior aesthetic, so perfect for boosting the brand visibility. We can do any type of shape. We can really go almost anywhere in the customization, and ultra small form factor possible also for seamless integration. And we are very robust, and we can work even at temperature as high as 150 degrees, and it is easily scalable in the sense that it is compatible with mass manufacturing equipment like pick and place and reflow oven. So if you want to have more information, so you can visit our website, but also you can send us email for technical inquiries or commercial inquiries. So thank you. And now I think we can move on to the Q&A session. Stop sharing.
Yeah, that's correct. Thanks, Julian. So first of all, thanks again to all the participants in joining the second webinar of the Amanda project. And besides the card, we also covered some more deep dive into the temperature sensor and the PV energy harvester that is used in this project. If you have any questions for any of the speakers, please use the Q&A button at the bottom of your screen. There you can submit your questions, and then we'll make sure that I'll pass them along to the right speaker. Also, if you have not yet taken the opportunity to fill in the poll, please do so before the end of the session, as it will give us valuable information for any additional webinars that we are going to organize. So if the speakers can also switch on the camera, then I think that is, makes it a bit more nice. Thanks. So first question, I think for you, Julian, about the PV harvester. So you mentioned you showed a system with the harvester and a power management IC and a battery. Are there any specific requirements for the power management IC and a battery that you connect to your energy harvester?
There are some requirements in terms of current capability of the battery, and there is also some current requirement in terms of what the load requires. If the load requires like too much current compared to the capability of a PMIC that is used in our Forever Last 2.0. But really depends on the load. So most of the vast majority of IoT devices will be completely compatible with what we have sized.
Okay, thank you. That I think is a very clear answer. Then next question is for Martin. So you have talked about the temperature sensor developed for this project. Is it also available as a component, let's say, in your regular portfolio?
Yes, it will be a standard product available to everyone. Actually, we are just finishing the CSP, so the final package. We have tested the wafer, and we will just have to tape the CSPs and make them available as samples to customers. And later on, they will be available in volumes as well on request.
Any idea on the timeline that you can share?
Yeah, I mean, we have to have the lead time of I would say 4 months for just a rough indication for volumes. Samples will be available in a single to let's say a few dozen volume in already early next year.
Okay, great, thanks. And then let me see if there is anything else. Yes, I think this one I will ask Charis. So can you give a comparison of the Amanda card compared to other popular product solutions that already exist on the market? What are the features that distinguish the Amanda card from other ones?
I would say the focus of the project from the beginning on the miniaturization and the low energy consumption. So this makes it a good solution for cases where the energy autonomy it's very critical and important. And this is what distinguishes us from other projects. that we had a focus for these aspects, for the very small dimensions, for the low power consumption since the beginning of the project. And this is what we built all the components and the integrated system on top of this concept.
Okay, that's clear. Thank you. Those were all the questions for now. There's another one coming in. Is the temperature sensor performance measured done with the CSP package? Does the package stress have an impact? So Martin, that's a question for you.
Yes, the package can have an impact. So the CSP is basically the best possible because it has least stress. So for instance, if you package in a QFN in a plastic package, you will have the different materials which can have a stress or can produce a stress. We are measuring and calibrating the CSP on wafer in-house. So the calibration is done for CSP. And we will evaluate just after we have the CSPs diced. We will evaluate them in-house again to check the calibration on a number of samples, which gives us then the confidence or the certainty that the remaining CSPs are also going to behave as specified.
Okay, thank you. Then that's it for the questions coming in at this moment. If there are no other questions at this moment, then and any other questions would pop up in the future, please don't hesitate to contact us, either the speakers directly, or you can also find us at amanda-project.eu or amanda@amanda-project.eu by email. Yeah, I think, is there anything else, Charis? I will give the floor back to you then.
Thank you, Peter, for coordinating also this webinar. And I would like to thank everyone for joining this webinar for the Amanda project. I think that after the webinar concludes, a recording of the webinar and will be available for all the participants, and also will be available to answer any future questions that you have for the project in general or for any of the individual components. So thanks a lot, everyone, for joining this webinar for the Amanda project.
Thank you. Thank you very much.
Thanks. Bye-bye.
Bye-bye.